All right? So today we're going to talk about intermediate drives. And you notice the title of the session says, what goes on inside the box. And so what we're going to do, I've got my phone on. If you can't hear me or if you're having trouble hearing me, speak up. So that way I can talk louder. All right? What we're going to talk about is we're going to take a look at three things. We're going to look at something called Bernoulli's law, and then we're going to look at something called the affinity laws, and finally we'll take a look at how the drive interprets those two things, how those two things impact our drive. And you'll notice on the bottom of your screen it just came up, www.pentairlearningcenter.com. So for those of you that would like to go back and look at some of our webinars that we've done in the past, that's the website that you want to go to. When you get there, if you're not already registered, it will ask you to register. So you register. Joan Zolmer is our keeper there, and what she will do is she will send you a sign-in. Once she sends you a sign-in, you can go in and you can look around. It talked about the past webinars where you can go in and view them, listen to them. There is an online e-learning that you can do that we've got set up for you. And also, there is a live webinar session so that you can pick which live webinars you want to attend. And in doing so, what will happen is we'll send you a reminder of that particular webinar. All right? And lastly, of course, there's live classes. We do 2 water systems classes and 2 ag and industrial classes a year up at the factory, and certainly would like to invite you to the factory school. Good deal. All right? And you get all that by going to the Pentair Learning Center. So if you want a little more, that's where you want to go to. All right? Now, we're going to start out with a section called Bernoulli's Law. Bernoulli was a mathematician and scientist who lived back in the late 1600s, early 1700s. Okay? He was a scholar. His whole family was scholars. And he wrote some laws. One thing that Bernoulli noticed was that water is non-compressible. And so he wrote a law about water being non-compressible. So if you look on your screen there, you're going to notice that we have what's called a cubic foot of water. And you notice if we want to put that cubic foot of water through that square foot, and we want it to go through there in 1 second, it's got to move at a velocity of 1 foot per second. If we take that same cubic foot of water, because water is non-compressible, if we put it through a 1/2 foot by 1/2 foot, and we want it to run through there in 1 second, it's going to be moving at a velocity of 4 feet per second. All right, and this is all because water is non-compressible. So a cubic foot of water always takes up a cubic foot of space. All right? Now, an example, and by the way, if you have the Berkeley B9020, which is the engineering handbook, get that out. We're going to use that a little bit, okay? So you can get that out. And basically, I'm going to put it up on the screen too, so you'll see it one way or the other. In our example here at Bernoulli's Law, we're going to take 200 gallons a minute, and we're going to put that 200 gallons a minute through a 2-inch pipe, and we're going to put it through a 4-inch pipe. Okay, now notice the pipe is PVC. Of course, the first question you got to ask is, how do you calculate the area of a 2-inch pipe? Now, of course, if we really think back in the reaches of our mind and go back to when we were in high school, for some of us this might be a really long time ago, all right? We're going to remember the formula pi r squared. Now, of course, some of us say, well, now, wait a second, I learned a long time ago, pi r round, take r squared. That's just a little humor, very little. And, of course, when you look at that, we're going to say, okay, if it's pi r squared, what I have to do is this. I have to know what the ID of the 2-inch pipe is. And the ID of the 2-inch pipe is 2.067. All right? Now, when we're doing pi r squared, what we do first is we take that ID and we divide it by 2 so we can get R. And you can see here, R is 1.0335. All right? And yes, I'm going to be very annoying for this first part of this problem, and I'm going to read a lot of numbers off. Okay? Remember it says pi r squared, so we're going to square that number, and so we take 1.0335 times 1.0335, and we come up with 1.06812222. All right? Now what we do is we multiply that by pi. Pi is 3.1416, and of course now we get the area of the 2-inch pipe, and it comes up to 3.3556128, which will round off to 3.3 square inches. All right? Now, of course, again, jokingly I said, well, yeah, pi r round, take r squared. The bottom line is that there's 2 ways of doing this formula. The second way says, let's talk about I mean, how many of you talk about pipe as a radius? I don't think anybody does. I've never had anybody raise their hand up and say, yeah, I talk about it as a radius. We talk about pipe as inside diameter, ID. So let's show you another way to get the same results. We're going to take the diameter and we're going to square the diameter. That gives us a number 4.27. Okay? Now we take that diameter times pi. Remember, pi is 3.1416. And we get 13.422. If you divide that by 4, you get 3.355, or 3.36 square inches. All right? So either way you do it, you're going to get the same answer. If you just assume make it into radius, that's fine. I mean, when you think about it, the process is the same. I'm either dividing the radius by 2, or I'm taking the total number here. If I use the diameter, I take that total number divided by 4. So the process, the number of steps, is the same. And the results is going to be the same. So you choose how you want to do it. All right? If we take the ID of the 4-inch pipe, we're at 4.026. So the formula looks a little bit like this. 4.026 squared times pi divided by 4, and we wind up with 12.73 square inches. Now, I want you to truly be aware of what Bernoulli is teaching us here, okay? Because if you look very carefully, what we did was we went from a 4-inch pipe to a 2-inch pipe, which most people would say, well, you're doubling the size of the pipe, all right? In reality, if we look at the area of the 2-inch pipe and compare that to the area of the 4-inch pipe, what we really did was we really almost quadrupled the pipe in size, okay? So even though it looks like we double the pipe size, we really almost quadruple that pipe size. And of course, that's going to affect the flow of the water through the pipe, all right? So again, if we look in our Berkeley Engineering Manual, it's going to give us the answer to these questions, because the question is, if I've got 2-inch PVC pipe, which has an area of 3.36 square inches, and I put 200 gallons a minute through it, what's the velocity in feet per second? So here is the page. It's page 8 in your engineering manual, all right? And you're going to notice that we're talking Schedule 40 PVC. Schedule 40 PVC is the same size as steel pipe. So that's why we're using that, all right? And of course, if you look over on the left-hand side of the page, it says gallons per minute. It starts at 2 and goes all the way down to 600, all right? Then it goes across the top, 1/2 inch, 3/4 inch, 1 inch, 1 1/4, 2, 2 1/2, 3, 3 1/2, and 4, all right? Now, I've highlighted the 2 and the 4 for a reason, because those are the ones we're going to use. If you look at that 2-inch column, you'll notice each of the pipe-sized columns are broken up into 2 columns. One is going to give you the velocity of the water as it moves through the piece of pipe. The other one is going to give you the friction loss of that water moving through the piece of pipe. Now remember, friction loss is something that you're paying for, and not getting any use out of. The formula that we're using is based off of Williams and Hazing's formula, which says every 100 feet of pipe is going to have the same friction loss. So you'll notice there it says that it's 100 feet of pipe. All right? So if you look at the half-inch pipe and go down to 20 gallons a minute, you'll see it says 5-inch pipe. If you go to the 3/4-inch pipe and look at 40 gallons a minute, you'll see it says 6-inch pipe. And of course, you can see there's an angle at which the pipe is now going to run. Okay? If you go down to where it says 200 gallons a minute, and you take a straight edge and lay a straight edge right straight across there, and we look at the 2-inch pipe, we're going to see that the velocity in 2-inch pipe is 19.1. 19.1. If you look at the 4-inch pipe, the velocity is 5.11. So let's go back to our slide and let's fill those numbers in. 2-inch pipe is 19.1, 4-inch pipe is 5.11. And again, I'm going to try and help you to understand what is happening here. All right? We're doubling the size of the pipe, which actually almost quadruples the area. The flow rate stays the same, and so what happens to velocity? It changes by almost quadruple. Does everybody understand that? Is there any questions about that? All right? So now, the next thing I'm going to do is I'm going to combine two different charts. We're going to use that chart that we just looked at, and then I'm also going to use the steel chart, which is on page 3. All right? The flow range we said was 200. We said that in 2-inch PVC, the velocity would be 19.1, but in 4-inch PVC, the velocity is only 5.11. All right? Now, the pipe size for steel pipe and PVC, Schedule 40, the ID is the same. And that's very important that you understand that. The ID is the same for Schedule 40 PVC and steel pipe. So if we go to page 3 in the engineering manual and we look, you're going to notice it starts out here. There's your 4-inch ID pipe. Down here it says 4-inch OD. All right? So, of course, what kind of pipe do most of you use? ID or OD? Okay, the answer most people give me is ID. So whenever I talk about steel pipe, I'm always going to talk about the inside diameter of the pipe. The reason for this, when you've got OD pipe, you're going to notice that the inside diameter changes. If you look at your 4-inch pipe, the inside diameter is 4.026. If you look at your OD pipe, the inside diameter is only 3.826. So there's a big difference between those two, and since most people only use ID pipe anymore, we're going to talk about ID. We're not going to talk about OD. Okay? So you'll notice in each of the columns, we're looking at the 2.5, the 3, and the 4. In each one of those columns, it says gallons per minute. So it's not like the other chart where I just go over the left-hand side and go straight down. Here, each one of them has their own flow rate in it. Each one of them has their own velocity in feet per second. Each one of them has what's called velocity head. Velocity head. I'm going to show you that formula in just a minute. You don't need to remember it. But basically, velocity head says we're going to take that flow rate, or that velocity moving through there, and we're going to convert it into an energy form that we can use. And, of course, in pump language, the energy form that we talk about is head. All right? And then the last column there is the amount of friction loss in each one of those pipe sizes at different flow rates. Okay? So if we take our 4-inch pipe at 200 gallons a minute, you're going to notice that the velocity is 5.05. So we'll fill it in there. And, of course, what we see is this. As long as the ID of the pipe is the same, the velocity will be so close, we're not going to notice a difference. 0.06 hundredths of an inch, or a foot per second, is what we're talking here. And I don't think anybody without real special equipment is going to be able to tell 0.061 of a foot per second. All right? Now, the next thing that we want to point, because the point that we're making here is that as long as the ID of the pipe is the same, the velocity is going to be the same. But the type of pipe does affect what we call friction loss. And so if we go back to page 3 again, and we look at that 4-inch pipe, 4-inch ID pipe, and we look at 200 gallons a minute, we find the friction loss to be 4.3. So we'll fill that hole in with 4.3. Now we go back to page 8, and we look at the PVC pipe. Again, we're going to 4-inch pipe, and you'll notice that the friction loss here, using the same formula here, is 2.06. So we'll put 2.06 in there. And again, part of the point that I'm trying to help you to realize is that even though the velocities are almost the same, the friction loss in plastic pipe is about half of the friction loss in steel pipe. Now, I'm not telling you to use plastic pipe. Please do not interpret it that way. That's not what I'm saying. What I'm saying is, whichever pipe you choose to use, make sure that you use the right friction loss for it, because it can affect how the pump is going to work. All right? Now, it's very important to remember that energy can neither be created nor destroyed. It can only be changed. So we're taking energy from one form and converting it to another form. All right? Now, again, remember I said head in our industry means the energy. So we're going to look at the formula for velocity head or velocity energy. And the formula, again, you do not have to, don't panic on this one, you don't have to memorize. Here's what it is, though. V squared divided by 2G. All right? Now, V is the velocity of the water moving through the pipe. We saw how to find that. Whether we got steel pipe or plastic pipe, we saw how to find that. All right? G is the universal gravitation constant. And what G means is 32.2 feet per second squared. So I can rewrite this formula, and I can say V squared divided by 64.4. All right? Now, I'm going to do something that I would never recommend you to do. I'm going to say, let's put 400 gallons a minute through a 3-inch ID steel pipe. The reason that I wouldn't ask you to do this really is because if you look down here, now we're on page 3 again in the engineering manual. If you look here, we're in the 3-inch pipe, and there's your flow rate, there's your velocity. So we come down to our flow rate of 400, and you'll notice your velocity, 17.4. So remember the formula. V squared. So 17.4 times 17.4 is 302.76. Divided by 64.4 equals 4.7012.422. And of course, we're going to run it off to 4.7. And also, if you look back in that 3-inch chart, you're going to notice the third column says velocity head in feet, and it comes up to 4.7. So we just proved to you that this is how you calculate velocity head. It's already done for you in the steel pipe, and the reason I'm pointing it out, because remember, as long as the pipe ID is the same, the velocity is the same. If the velocity is the same, the velocity head will be the same. So if you're working in that plastic chart and you say, well, I can't figure out velocity head, you don't have to. Just find the same size pipe in ID in the steel charts, and you'll be able to know what the velocity head is because it'll tell you right there in the third column. All right? Now, Bernoulli's equation, and again, I don't want you to panic. You don't need to know this. It's in some of the books that we sell. So there's books out there you can find this equation. The equation simply says this: capital P1 divided by small p plus v squared 1 divided by 2g plus z1 is equal to capital P2 divided by small p plus v squared 2 divided by 2g plus z2. Now, there is a user-friendly version of the formula, and it looks like this. Capital P plus v squared divided by 2g plus or minus z equals a constant. Equals a constant, okay? Basically what it's saying is this. You'll notice it had P1, v squared 1, and z1. 1 is a point on our system. And then it says P2, v squared 2, and g2. Those are also points on our system. So that's another point on the system. And all we're doing is we're comparing the 2 points. Remember, z is the height above or below. So we pick point 1, and then we look at point 2, and we say, is point 2 above or below point 1? Or are they the same? And that's where you're getting the formula at. And it's saying that this energy that's in this pipe is going to be constant no matter where you go. However, things will change. So as long as the pipe size, and I'm talking about the diameter, when I talk about pipe size, I'm talking diameter. As long as the pipe diameter is the same, the velocity has to remain the same. All right? It can change if the pipe size changes. So, all those things, what do they mean? Capital P is the pressure gauge reading in feet. We always like to talk in feet because our pump curves are in feet. The small p is the density of the liquid being pumped. Now, of course, if I was to take a butter churn, I put milk in there, cream in that butter churn, and I churned, and I churned, and I churned, and I churned, eventually what's going to happen? The cream is going to turn to butter, and it'll get thick, all right? But if I put fresh water into a pipe, what's going to come out of that pipe, no matter how far away it is? Fresh water. So, of course, the density of the liquid being pumped, as far as we are concerned, doesn't mean anything, and that's why it's taken out of the user-friendly version, because we're putting fresh water in, we're getting fresh water out. V squared divided by 2g is the velocity head formula. We talked about that just a minute ago. And the last thing is z. Z is the height above or below a reference point. So point 1 is one reference. Point 2 is a different reference, and is it above or below point 1, or is it equal to point 1? All right? Now, this is what you're going to see in a piece of pipe. If you have a small piece of pipe, and when I say small, I mean small diameter, you're going to, and you put a high velocity water through there, a lot of water through there, the velocity is going to be up, and the pressure is going to be down. When you move from that small pipe into a bigger pipe, what's going to happen? The velocity is going to go down, and we're going to convert that velocity energy that we had into pressure energy. So we'll have more pressure in that bigger pipe. Once we convert it back into a smaller pipe again, what's going to happen? The velocity is going to go back up, and the pressure is going to come back down. Real life numbers, okay? The first pressure gauge is 8 psi. Remember, the second pressure gauge is going to read up, and so now we're 16 psi. In real life, because of friction loss, that third pressure gauge is going to read less than what the first one did. All right? According to Bernoulli, it's all the same because he's measuring velocity head. He's not measuring friction loss. We're measuring friction loss. So that's why those pressures are a little different. But as long as we know that friction loss, it's energy we can add right back in. And that's the point. Okay? So if you look at Bernoulli's law, simply we say, okay, I want to put 400 gallons a minute through a 3-inch ID steel pipe. We already said the velocity head is 4.7. if we give you a pressure gauge reading of 10 psi, that's going to be 23.1 feet of head. So I add 4.7 to 23.1, and remember what Bernoulli's telling us, all the answers must remain the same. So all the answers are going to be 27.8. Now if we move this into a 4-inch pipe, so we're going to take this and we're going to put it into a 4-inch pipe now. So we look at 4-inch pipe, 400 gallons a minute, the velocity head is 1.6, all right? So if my velocity head is 1.6 and my total head is 27.8, what is my pressure gauge reading in feet? And all you have to do is subtract 1.6 from 27.8, and you get 26.2. So that's going to be my pressure gauge reading in feet. And you can notice that it did go up when we went from the 3-inch pipe to the 4-inch pipe. When you go back to the 3-inch pipe, the velocity is going to go back up, so the velocity head is going to go back up. And of course, with the velocity head going up, the gauge pressure is going to go back down to what it was originally. Anybody have any question on that? Now, the affinity laws can be a little tricky. I learned them 21, 22 years ago, something like that. And I remember when the trainer taught them, he said, RPM1 divided by RPM2 equals GPM1 divided by GPM2. Everybody got that? And we moved on. And I'm like, no, I didn't quite get what you meant there. So I promised myself that when I was going to teach this, I was going to make sure everybody understood what it meant. So here's what it means. If I know 3 parts of this formula, I can calculate the 4th part. So I know the RPMs that it takes to get GPM1. I know the RPMs I want to go to. So I take RPM1 divided by RPM2. Whatever the answer is, I multiply it by GPM1, and I get GPM2. I, of course, can go in the other direction. If I know the flow rate that I have and the flow rate that I want, I divide the flow rate that I have by the flow rate that I want. If I know the RPMs that I'm getting at that flow rate, I just multiply the RPMs by the change in the flow rates, and that's going to give me my new RPM. Any questions about that? Now, here's the point. Flow rate is a 1-to-1 ratio. That makes it real easy to do. When you get to total dynamic head, or TDH, it's changed by the square of the difference in the pressure. So, again, if I know all 3 things here, okay, I know RPM1, I know RPM2, and I take RPM1 and divide it by RPM2, multiply that by TDH1, it'll give me TDH2. You can work it the other direction, although I am going to just caution you that that can be a little difficult, because now I take TDH1 divided by TDH2 and I find the square root of it before I can multiply that by RPM1. But that's still easy compared to brake horsepower, and that's because brake horsepower is changed by the cube of the difference, the cube of the difference. So I know that at RPM1 I get brake horsepower 1. I want to move to RPM2, but I know how much brake horsepower it takes for me to get there. So I divide RPM1 by RPM2. Whatever the answer is, I multiply it by itself, and then I multiply it by that same answer again. And then I multiply that by brake horsepower 2. If you really want to go the other way, I'll give you a hint. Cube roots. And that usually scares people off. But you just have to find the cube of the difference between BHP1 and BHP2, and then multiply that by RPM1. All right? Notice what it says here. These equations are quite accurate for changes in speed with limits from 50 to 200%. So if I'm messing around with speed changes, it's much easier than if I am messing around with diameters. And the reason I'm saying that is because sometimes we trim impellers, and when we trim impellers, you're stuck to a 10%. And so when you're stuck to that 10%, if you go over that 10%, you're going to wind up with I don't know what. And the reason being is this. When you trim an impeller, you change the shape of the vane, and that's what changes the speed of the water. So that's why we got to watch that. Remember, we're looking at peripheral speed, so this chart says the effects of change of peripheral speed on characteristics of centrifugal pumps. Now, of course, we're also talking about variable frequency drives, and so the bottom line comes down to this. I'm going to talk about RPM speed because that's what the drive changes, is the RPM speed. But remember, when I say speed, what we're really calculating is the peripheral speed. So you'll notice on the chart here, there's N, which stands for speed, Q, which stands for flow rate, H, which stands for head, and HP, which stands for horsepower. And you can go up or you can go down. Either way, it doesn't matter. All right? So to do an example, we're going to change from 1,800 to 2,100 RPM. We're going to go up in speed. Now, again, that changes the formula a little bit. Our number is going to be greater than 1 instead of less than 1. Okay? But we need to know the performance at one of these two in order to calculate the other one. So if we know that at 1,800 RPM, we're getting 600 gallons at 70 feet ahead, requiring 15 brake horsepower, what's going to happen at 2,100 RPM? This is the answer here. First thing you have to do is you have to calculate the change difference between 1,800 and 2,100 RPM. In this case, it's 300 RPM. And then what I do is I divide here. So I divide the 1,800 into the 2,100 because I'm going up the speed. And that gives me a number greater than 1. And now I've got my constant, which is 1.167. So in other words, I'm changing this speed by a little over 16%, not quite 17%. All right? Remember what we said, flow rate was a 1-to-1 ratio. So I take my flow times 1.167, and I get an answer of 700. It's 700 plus a couple tenths of a gallon. So for all practical purposes, we'll call it 700 gallons a minute. Remember that the head is changed by the square of the difference. So if the head is 70, I multiply that by 1.167 times 1.167, and now I'm getting a total head of 95. And so far, things aren't so bad. But let's look at the cost. Because when we're going up in speed, that's what we're doing. We're increasing our horsepower requirement. By how much? Well, let's take a look. If it's 15 horsepower at 1,800 RPM, so you get 600 gallons a minute, I multiply it by triple. So I take 1.167 times 1.167 times 1.167 times 15, and I come up with 23.8 brake horsepower. In other words, if I don't have about 24 horsepower, this motor is not going to be doing good. Everybody understand that? Now, the next thing we're going to look at here then is we require 23.8 brake horsepower. What do we know about motors? Well, we know that if we take the nameplate horsepower times the service factor, that will give us the service factor horsepower, which is the maximum horsepower the pump can sustain. So if we take our 15 horsepower pump and multiply it by a standard multiplier of 1.15 service factor, we wind up with 17.25 brake horsepower. Now, if I apply 23.8 brake horsepower to a motor that can only do 17.25, what's going to wind up happening? I'm going to burn up the motor. Okay? So let's go with a 20 horsepower. A 20 horsepower times 1.15 is going to be 23 brake horsepower. Now what winds up happening? I still burn up the motor, just a little bit slower. Okay? In other words, to fulfill the requirements of this change, we need a 25 horsepower motor attached to our 15 horsepower pump, and you can see why, because it's going to give us 28.75 brake horsepower, which is more than the 23.8 that we need. You can begin to see here, and what I'm hoping that you're going to understand, is that it is easier to start high and go low than it is to start low and go high. Because when I go high, now I got to say, well, geez, can I find a motor that's going to fit? Because remember, we're looking at a NEMA standard motor here. Will that motor fit my NEMA standard pump if the pump is set up for 15 horsepower? The likelihood is that's going to be tough. Okay? So, motor recommendation for variable frequency drives. We've talked about Bernoulli's law. We've talked about the affinity laws. Now let's get into the drives themselves. We're going to recommend for above ground pumps that you use a premium efficiency motor. What a premium efficiency motor does is it builds in a little extra service factor that it doesn't tell you about. Okay? So premium efficiency motors are going to have a little more oomph in them, and you can abuse them a little bit more and not bother them quite as bad. All right? The length of the wire from the drive to the motor has an impact on the motor. And the reason for that is because just like if we have a long piece of pipe and somebody slams the valve shut on that piece of pipe, we get something called a water hammer. And water hammer will hit and then come back, and then hit and then come back, right? You can raise the pressure by 10 times by slamming a valve shut. Similarly, when we're talking electricity, what happens is when that sine wave hits, if it hits at just the right point, we can raise that sine wave above what the voltage of the motor can handle. And that's what's going to get delivered to it. So we're going to talk a little bit here about filters and reactors, because filters and reactors can help bring that sine wave down and eliminate some of that hit. All right? So when do we need a filter or reactor? If your lead length, in other words, from the drive to the motor, is over 150 feet. If the cost replacement to change the motor out is prohibitive, typically that happens around 30 to 40 horsepower, and we begin to say, geez, you know what, at 40 horsepower, I can almost rewind the motor cheaper than I can buy a new one. So when it starts getting cost prohibitive, that's when you want to say, maybe I need to put that on there, okay? And then lastly, any time that you have a submersible motor that is over 230 volts. Now, I know some of you are thinking to yourselves, well, geez, submersible motors are only 230 or 460. But that's not true. That's only in America, okay? That's in Canada, that's in Mexico, that's in the Caribbean, all right? But the bottom line is the rest of the world all runs on metrics, and they use a 380 volt system. So a 380 volt system is greater than 230 volts, and the bottom line is you can now get that sine wave to really peak up there and hurt things. So that's why we say any submersible motor over 230 volts, you should be putting something on it. Okay? Why do people use a variable frequency drive? It's going to reduce costs. The main reason anybody uses a variable frequency drive is they're trying to save money. Yes, they put a big initial investment in, but they're expecting to get money back for their investment. And if they do things right, they will. Okay? The affinity law says that the impeller diameter is held constant. I can change things around. For example, if I know the flow rate at Q1 and I know the speed it takes to get to that flow rate. If I want to find the flow rate at Q2, I just divide Q1 by Q2. I multiply that difference into N1, and that's going to give me N2. Okay? Now, of course, remember we said pressure was changed by the square. So I take the speed at N1, I get the head at N1, I take the speed at head 2, or at speed 2, and now I square that difference. So I take N1, I divide it by N2. Whatever the answer is, I multiply it by itself, and then I multiply that by the head, and that gives me head 2. Remember, power is changed by the cube of the difference. So I know this speed, and I know that I'm going to take that much power to get to that speed. I know this speed, but I don't know how much power it's going to take to get there. So I divide N2 by N1, multiply it, cube it, multiply it by itself 3 times, and then, of course, I multiply that by my pressure, and that gives me a rather large number. Okay? Another simple way of looking at it is right here. We're going to use watts instead of for power here instead of horsepower. So here's the formula here. P1 divided by P2 equals N1 divided by N2 cubed. All right? So P1 equals 1,800 RPMs. And N represents 60, N1 represents 60 hertz, and N2 represents 50 hertz. The formula looks like this. And I'm going to take 60 hertz divided by 50 hertz. I'm going to cube the difference, and that's going to give me an answer of 1.782. I multiply 1.782 times 1,800 watts, and I come up with 1042 watts. Now you'll notice that's 58% of the 1,800 watts. Here's the point that we're trying to make. Anytime that you are sizing a system, you size the system at 100% of the maximum the system is going to need. Anything under that is savings. And so that's why we recommend you do it that way. If you pick 60 hertz, that's 100%. If I work at 50 hertz, that's only 58%. If I work at 40 hertz, that's only 30%. I'm saving 70% of the energy that I would have used had I not had a variable frequency drive. I was going to cross the line starting. Okay? So that's why all that is so important. Now, how does the drive work? And this goes, I was talking to Ted earlier today, the way this goes is it doesn't matter what the drive is. Okay? It doesn't matter whose drive it is. If it is a variable frequency drive, the way that it works is this. It takes AC power in. Now that's an AC sine wave right there. You can put 3-phase power in. You can put single-phase power in. If you're going to put single-phase power in, the point to remember is you have to allow for double the amperage of the load that you're trying to move. Okay? So now I go into the drive and I go through something called a rectifier. And what the rectifier does, it takes that plus and minus sine wave on the AC signal going in, and we run it through a DC bus, and you can see it cuts it in half and turns it over. Then what it does is it runs it through a set of capacitors. And as it goes through those capacitors bring it fine line down to what we call DC current. Remember, DC current is running in one direction and one direction only. There's no more AC here. Okay? So we take it, we run it through our DC bus, our filter, and that's our capacitors, and that brings it down to a straight line. We get that flat line to run into what we call IGBT switches. The IGBT switches are going to turn off and on 8,000 times a second. At 8,000 times a second, what we're getting out is called pulse width modulation, or PWM. It's not DC voltage, it's not AC voltage. And the way you know it is look at what pulse width modulation looks like. You'll notice if you look way back over on the left-hand side, there's your AC sine wave. And your AC sine wave is a nice smooth up and down and back up and down again, okay? When you look at pulse width modulation, it's choppy. What it's doing is we're turning on and then off, and then on and then off, and we're changing that DC voltage to go up. We're turning it on, then we're turning it off. Then we're turning it on, then we're turning it off. And we're getting a spike that goes up and down, okay? So you've got to make sure that you get that sine wave to look proper. Okay? So if you watch my sine wave here, if you watch my sine wave here, you're going to see we're doing this at 250 volts in 4 milliseconds. That's what this picture is. Basically what we did was we took a 40-foot lead and we hooked it up to the drive, and then we hooked it up to an oscilloscope. And these are pictures that come right off of the oscilloscope. Okay? So now what we're going to do is we're going to turn on and off. So we turn, there's our DC current coming out, or DC voltage, okay? And we flip it on and then off, and then on and then off. The length of time that it stays on versus the length of time that it stays off is going to give me my hertz, okay? Typical voltage, you'll notice there it says typical voltage on a 250 volt system is a 2.6 spike. If we're getting a 2.6 spike times 250 volts, that's 650 volts. A normal regular motor can handle 900 volts. A premium efficiency motor can handle 1,000 volts. So if this is what we're getting, big deal. But notice what happens. You can get a spike in there every once in a while that is going to be 3.5 times the voltage. So now we're up to 875, and we're really pushing the limits on that standard motor. So this is why on a 40-foot cable, a premium efficiency motor is best. All right? Now what we've done here, we've changed things a little bit. We're still going to be at 250 volts in 4 milliseconds, but what we're doing is we are going to go with 140 feet of cable. And you'll notice here, look at those spikes there. They are 4.6, which puts us at 1,150 volts. At 1,150 volts, we're going to be blowing up, or burning up, premium efficiency motors. So this is why that filter or reactor are so important. Okay? Here we are at 240 feet of cable, and here we are at 1,040 feet of cable. 1,225 volts. We're burning up any motor we put in there. Okay? If we don't put a filter or a reactor on there. Now, if you look at this, you'll notice this is the sine wave for a 40-foot length of cable with, 140-foot length of cable with a reactor on it. And by putting a reactor on there, basically what we do is we bring that sine wave down, and now we're at about 900 volts. Again, you're pushing the limit for a standard motor, probably a premium efficiency motor here. You'll notice, though, that before we put our filter on there, our reactor on there, it was 1,150 volts. So we've really made some changes there. This is what a reactor looks like, and all it really is just a set of coils. So we're putting some coils in there, we're running the electricity through the coil, and then sending it out. And as we do so, what that does is that coil reduces the voltage going out, the line voltage going out. All right? Now, when do you use what? And you'll notice here we've got 3 different ways. We're talking about a NEMA, above ground, standard efficiency motor. Then we're talking about a NEMA above ground premium efficiency motor, and we're talking about submersibles. You'll notice if you're 50 feet or less, the only one that really needs anything is that submersible, and it's going to require a reactor. if you're at 50 to 150 feet, the standard motor is going to require a reactor on 230 volt along with the submersible motor, and all the motors are going to require a reactor the above ground motor is going to require a reactor on 460 volt. The submersible is going to require a filter. Anything over 150 feet and everything requires a filter. Okay? Now, what a filter does is a filter brings it down even more. So here's that same 140 feet, and notice now our spike is only 750, which means we could use a standard motor as long as we use the reactor. Okay? So, when you look at your 1,040 feet, we're at 850 volts. Geez, look at that. We can even use a standard motor here as long as we put a filter on it. Now, what does that filter look like? Well, if you look at the filter, it looks like this. It is a set of coils, the same as we saw before, only now we're also going to add a capacitor pack to it. And so we're going to run each one of those through a capacitor pack and then to the motor. Basically, your filter or reactor gets hooked up on the discharge side of the drive. So you hook up where you would go to your motor, you hook up there, bring it out, put it to a reactor, and then run it down to the motor. Or hook it up to a filter and then run it down to the motor. That's what your filter reactor is going to do for you. All right? Now, I talk about this in several of my drive trainings simply because of the fact that this is a multimeter that really can help you. This is called a Fluke 87V. Fluke 87V. When you look at the Fluke 87V, it's used to correctly measure the voltage on variable frequency drives. Remember, what's coming out of a drive? Pulse width modulation. You're not getting AC voltage, you're not getting DC voltage, so you can't measure either one of those because they're going to be wrong. Okay? If you were to put this on AC voltage and stick it on the outside discharge of your drive, it would probably read close to 100 volts more than what your motor is actually seeing, because it's measuring the whole square. Okay? When you press that low-pass filter button, which is something special on this multimeter, when you press that low-pass filter button, it's going to sort out or only look at what the motor is seeing. Okay? So you set your dial for AC voltage, which is right there. Then you push the yellow button, which is up here. That yellow button turns on the low-pass filter. All right? If you look carefully on the drive, it's going to mention there that you've got the low-pass filter turned on. All right? Now when you take your measurement, you are getting the voltage that the motor is seeing. And that's what's nice about this Fluke 87V. I'd like to say I sell it. I don't. But I did go online and I found it for $465. I carry one every place I go. I carry a Simpson 372 and I carry this multimeter. If you're going to invest in a multimeter, you might as well buy the one that's going to help you the most, and this is the one that's going to help you the most. All right? Now notice here it says if the low-pass filter is not used, the reading will be significantly higher, approximately about 100 volts. It's a 1.414 ratio is what it really is. So if you take your incoming voltage, multiply it by 1.414, you should get approximately what your outgoing voltage is if you're running on AC voltage. If you're hooking up a low-pass filter, you'll see what you're supposed to see. All right? Now, I want to talk a little comparison here between the PPC-3 and the PPC-5. And when you look at them, you're going to notice that the horsepower rating on the PPC-3 is 1 through 30 horse. The horsepower rating on the PPC-5 is half through 200 horse. The voltages, The PPC3 is only set up to be run here in the United States or in Canada as long as they don't require 575, because it won't go to 575. The PPC5 is set up so that you can run it at 575 volts, which up in Canada, sometimes that's what they do. Okay? Your frequencies are going to be 50, 60 hertz. Okay, either one of them. There is a float choke on the 5, not on the 3. The float choke checks the incoming voltage, and it brings that voltage down so you don't wind up sending something back out that you don't want going out. Electric companies like that feature. That's a good feature. Okay? Your number of relays, the PPC3 has 1. The PPC5 has 3, but can be extended to 6 if you do things right. Okay? Now, when you look at the PPC drives, all right, you see the PPC5 there, it says NEMA 12, and then it says PPC5 in the middle, NEMA 1, and the last one says PPC3. Okay? They look very similar. There are some differences in them. When you talk about NEMA 1, you're going to see these slots in the side of the drive. What those slots do is they allow for the drive to breathe, which means this needs to be used in a room that's not very dirty. Okay? If you've got a room that's very dusty, now you want to use the PPC5 NEMA 12, because the NEMA 12, as you'll notice, has no vents. The only opening for air to get into there is at the bottom. And there is a filter there, and it filters all the air that gets pulled through. Now, of course, that also means something else very important, and that is if you're going to be using the PPC5 with a NEMA 12 enclosure, you need to check that air filter every once in a while and keep it clean. The dirtier the filter gets, the hotter it gets inside that drive, and the more likely you are to trip it on overheat. All right? So, other reasons why people use variable frequency drive, they want to reduce costs. All right? It provides a constant something. For most people, that something is pressure. Some people, it could be a constant flow, but I'm going to show you an application here. This took place in Batavia, Illinois. And what they wanted here was a constant height. You can see the 10-foot level, and you can see we're at about 8.5 feet. So we're down about a good 1.5 foot of water. Okay? So if you look over here in the beach area of it, instead of the pool area side of it, you'll notice that what happened here is they built a swimming area over an old rock quarry. And of course, the problem that they had was they built the swimming area above the rocks. Well, the rocks hold the water in. But once you get above the rocks, the water flows out. So they would fill this thing up, and it would empty out. And they would fill it up, and it would empty out. And when you fill it up to 10 feet, and it empties out to 8.5 feet, it takes you a while to fill it back up again. Because you got to put 1.5 foot of water, and trust me, this was a big swimming area. Okay? So what they did was they did this. They put a hole in the wall, and they brought a 6-inch pipe over. You can see it came over maybe 1.5 foot or 2 feet. Then what they did, and by the way, those are not my feet, okay? Then what they did was they brought a 6-inch pipe straight up, all right? Now, the reason that they did this, when we first turned the drive on, the drive said, I think that the transducer is 2.9 feet below the point that you told me is my set point. And so the guy said, no, Bill, that's not possible. It can't be. He said, I'm sure that that transducer is wrong. So we went out there, and what we did was we popped the top on that 6-inch well casing there, and you can see they've got tie-downs to tie down that coil of wire and keep that transducer at a certain height in the 6-inch pipe. So I pulled the transducer out very slowly so I didn't move anything. I laid it on the ground. I said, okay, now measure from the bottom of the transducer to this tie. It was 3 feet. I said, well, I think 2.9 is pretty close. I think the drive is pretty close. So we put the transducer back down in there. Now, there is one thing that I want to point out that I would not do if I was you. I would not wind all that transducer cable up in there. I would cut the transducer cable short so that I would get an accurate reading. Okay? Because sometimes when you wind it up like that, you create a coil, and that could give you an inaccurate reading. All right? So there's your tie downs, and there's your bar. That was your set point. We're saying that we must be 2.9 feet below that point. All right? So here's your hookup, and on the left-hand side is your input. You notice it's, what is that, R1, V1, and W1, and your output is R2, V2, and W2. All right? So we hook it up. On one side is our input, on one side is our output. We did have 3-phase here, so we put 3-phase in. Okay? Now, this is 200 gallons a minute coming out. All right? Splashing into the pond. That's where the well is. I'm standing in the door where the VFD is of the pump house, and I'm taking a picture of the well way up there. It's kind of hard to see, so I zoomed in as close as I could, and this is what it looks like when you get on zoom. Now, there's a couple important things to note there. See that brass fitting there, that brass ball valve that comes out? That brass ball valve was there in case they wanted to fill up a water truck. So if one of the Batavia water trucks pulled in here, what they would do is they would close that big valve there, and after they closed the big valve, then what they would do is they would open up the ball valve. All right? They would fill up the truck, and then they would close the ball valve down. Now, if they didn't open that big valve back up again, we were in trouble because the pump would eventually deadhead, and we'd have a lot of problems. So they also put a transducer up here, and we actually had 2 transducers in this system. When we put the second transducer in, we brought it down, and it's a pressure transducer, and it's hooked up here. And basically what it's doing is it is reading the pressure here. And if somebody forgets to open up that valve, and they've got the other valve closed, the drive says, you know what, we're hitting the pressure we're supposed to, we better go to sleep, and it would put the drive to sleep. It was just a safety precaution so that guys wouldn't forget to do what they were supposed to do. All right? Now, other reasons then, we want to reduce costs, we want to produce a constant something. We also get motor protection. Now notice what we're protecting against. You're protecting against ground fault. You're protecting against short circuit. You're protecting against phase loss and imbalance. You're protecting against overload. You're protecting against under and over voltage. That's because the drive has all that built into it. You don't need to. Now, normally when you do a 3-phase across-the-line system, you need to do an imbalance test. When you have a drive, you don't need to, because the drive makes the electric going down to the motor, and it balances each one of them out. You don't need to worry about that. If something should happen and one of the legs falls out, the drive shuts down. It's that simple. It will not single-phase or 3-phase motor and cause you to spend a lot of money. Okay? Other reasons to use a drive, if you are a pump and motor, it maximizes pump and motor functionality. If you are somebody who's a stocking distributor or a stocking installer, and you know how you used to have a big pump, and then you'd have a jockey pump to go with it, now you don't need a jockey pump in most cases. In most cases, you can slow the motor down enough to fill the pipe up and then turn the pump on full. Okay? Now, of course, you've got to check and make sure that that's going to work with every pump, because there is a minimum continuous stable flow on pumps. If you go below that minimum continuous stable flow, even if you've got a drive on there, you're going to have a problem. So check your minimum continuous stable flow before you say, oh, I don't need that jockey pumping. Okay? And then lastly here, it provides a soft start and stop. Soft start means that what happens is we bring the drive up slowly. The drive brings the motor up slowly. With an above ground motor, it takes 5 seconds to get up to speed. A submersible motor is differently made, and it doesn't come in premium efficient. So a submersible motor must be to 1800 RPMs in 1 second. That's a rule with the submersible motor. So because it's a rule with the submersible motor, you need to make sure that you're at 1800 RPMs in 1 second, and that's what the drive will do. Soft start simply means that we're going to slow the flow down and keep the pressure the same. Typically on a cross the line starting, when you slow the flow down, your pressure goes up and you get a spike. You get a water hammer. Okay? With a drive, you may not get a water hammer at all. If you do get water hammer, it is extremely minimized, and that's why a drive really helps you. All right? That's it for today. I will see you all again next time. Thank you so much, and I'm sure glad you were here. Bye now.